Hi folks, welcome to part one of the first Unit 5 lesson. So I want us to recall our old friend here, Broccoli Bear. And Broccoli Bear lived in a one-dimensional world, so he could only move forward and backwards. Okay. Now, the reason why this is important is we were able to describe the direction that Broccoli Bear was traveling by just using positive and negative. So if I thought of some reference point, so say my reference point was here, and we called this 0, we could say, well, when Broccoli Bear's on this side, his position is positive, and when he's on that side, his position is negative. And then we could look at rate of change, in other words, for the velocity. So when he was traveling in a positive direction, okay, in other words, the position was increasing, we could use, the derivative there would be positive. So a positive velocity meant moving to the right, and a negative velocity, where the position was decreasing, meant moving to the right. To the left. Okay, so everything could be described numerically. Okay, the problem becomes when we allow Broccoli Bear to live in a two-dimensional world. So Broccoli Bear is not just moving back and forth, but can move anywhere along a 2D plane. Okay, we see that positive and negative is not enough, because is positive and negative going in this direction, or is it going in that direction, or maybe diagonally? Okay, so we need a new way to describe motion when it comes to 2 dimensions. All right, now we can even take this further. What if we allow Broccoli Bear to travel in 3 dimensions? Well, first of all, I realize this is not going to be enough. All right, so we gotta, maybe make Broccoli Bear disappear for a second, and who knows where he ends up. And here, all of a sudden, Broccoli Bear ends up in a world where he can travel more than just back and forth. Okay, we notice that Broccoli Bear can now travel up and down and anywhere in 3D. So again, how are we going to be able to describe this motion? Clearly, again, just using positive and negative is not going to be enough. Okay, and so this is where we have to have a discussion about 2 very important terms that we're going to use to describe these motions. Okay, and we have to talk about the idea of scalar versus vector. Some of you have heard these terms before. In a little bit, I'm going to ask you to think about what you might know about scalars versus vectors, but there's some very clear differences between them. So instead of just asking what's the difference between a scalar and a vector, well, why don't we have the ultimate scalar versus vector smackdown? Okay, well, back to reality, and what I want you to do now is take your worksheet and hopefully stop the video and think about what the difference is between a scalar and a vector. And if you can also move on to number 2, and some of you have already seen this stuff, how can we represent scalar and vector quantities? All right, so take a moment, fill out numbers 1 and 2, and then we'll come back and look at it together. Okay, so we're back. So what do we mean by a scalar and a vector? So let's go back to Broccoli Bear here. Okay, so when Broccoli Bear was moving in 1 dimension, we really just needed a number in order to describe his motion, and it so happened that if the number was positive or negative, that gave us a little bit more information. All right, so if we said the position was 3, okay, well, 3 from a particular reference point, but if the number was positive, then we designated that as being 3 units to the right of the reference point. Whereas if we use -3, okay, it represented a different position, 3 units to the left of the reference point. Okay, so everything could be done using a number, even though that positive and negative did help us distinguish between these 2 directions. Okay, so we're going to need something much more when it comes to 2 dimensions. Okay, and what we need is this thing called a vector. Okay, and what a vector represents is it's something that needs to be described not only with a number. So to say that Broccoli Bear moves 10 centimeters doesn't tell you where he's moving. It doesn't give enough information, because do we mean 10 centimeters in this direction, this direction, that direction? Okay. In one dimension, it was enough to just indicate positive, negative, because he could only go back and forth. Okay, so what we need to do is we need to find a way to not only say that Broccoli Bear has moved 10 centimeters, we need a way to describe the direction in which Broccoli Bear moves. And so that's why we need the concept of a vector. So a vector is a quantity that contains both the numerical component, in other words, the 10 centimeters, but also the direction in which Broccoli Bear is moving. Okay, whereas what's a scalar quantity? Well, a scalar quantity is something that can just be described with a number. Okay, so if you think about it, well, something like time, the amount of time that elapses, well, doesn't matter what direction. Okay, it's just a numerical value. Okay, something like distance, if I just ask someone, okay, how far did you run today? They can say, oh, I ran 5 kilometers. That's enough information. Whereas if I want to know, well, where did you run to? Well, I'm also going to need some sort of direction. Okay, so a scalar, so let's write this out here. A scalar is a quantity, okay, that can be described with a number alone. Okay, so in particular, things like time, distance, these are what we consider scalar quantities, all right, where we just need a number. So how long did you run? 50 minutes. How far did you run? 10 kilometers. Okay. A vector quantity was a quantity that needs both a numerical value and a direction. So this is a quantity that can be described with a numerical value. Okay, so a number and a direction. Okay, so if we think about things that need a direction, well, instead of distance, what if we're talking about the velocity? Okay, so the velocity is not just how fast you're going, but it's also the direction that you're going. So it's not enough to say I traveled at 2 kilometers an hour. I traveled at 2 kilometers an hour in the north direction or in the east direction. Okay, something like force is also a vector quantity, because if I have some object and I say I applied a force of 10 newtons, well, it's important to know that I apply the force in that direction, in which case this is where the object ends up, or did I apply the exact same force in this direction, in which case that's where the object ends up. Sorry, I'll just maximize this here so it's easier to read. All right, so force is another type of quantity that needs both a number, so what force did I apply and in what direction did I apply it. All right, so next we're going to go to how we can represent a vector quantity. Okay, so we already know that a scalar, well, just a number. Okay, often with a unit, obviously. So if I'm talking about time, I would say, well, 20 seconds or 20 minutes. So a vector quantity, I need a way to incorporate this idea of direction. Okay, so one way, and by the way, the two that I'm going to specify aren't the ones that we're going to be using in the long run in this course. Okay, but we'll start with something simpler. So I would say the simplest way to represent a vector quantity is pictorially. And what we could use is we could use the arrow. Okay, now why the arrow? Because we can take the length of the arrow, which would represent the magnitude, and then the direction that the tip is pointing, well, that would just represent the direction. So we're actually very explicitly representing the direction of motion. Now, one thing you'll see me avoid at this point is representing vector quantities in 3 dimensions. And we're going to stick with 2 dimensions. We'll talk later on about how we're going to, the different options for representing these vector quantities in 3 dimensions, although the arrow could also work, because if I have the arrow, could be pointing up or down. It could be pointing in a 3D direction. Okay, so we will still use the arrow. We'll see that the second one that I bring up, not quite going to be as useful in 3D. All right, so what represents the magnitude? Well, that's just going to be the length of the arrow. All right. Now, what if I want to represent 200 newtons? Does that mean I have to have an arrow that's 200 units long, say centimeters or even millimeters? Okay, so as you would do, say, on a map, you'll often use a scale. Okay, so you can use a scale. So you could say, 1 centimeter represents 20 newtons of force. Okay, so remember, this is just a representation. There's nothing that says that the actual length has to represent the exact number. I can use a scale. Okay, and the direction, well, is just going to be the direction the tip is pointing. So what's great about this is that we can draw some nice pictures. So if I want to represent something moving in a particular direction and I want to give a sense of sort of the force, so something with this force in that direction, if I want to represent a bigger force in that same direction, I would just make a longer arrow, smaller force, smaller arrow. So very nice. However, not particularly nice to work numerically, especially if I have to start considering, measuring with a ruler every time. Well, okay, this length represents that force. So what we can also do is represent this more explicitly. Okay, and one of the ways that we can do this is to use a reference. Okay, in the same way that in 2D we used the number line and we use the 0 on the number line to represent a reference point. Well, I can do the same thing here, and what I use as my reference point is north, south, east, and west. Okay? So if I want to represent this same vector, what I do is I just place the vector at the center here of north, south, east, and west. Okay, and again, I can specifically say what the magnitude is. So say here I said 1 centimeter represented 20 newtons, so this seems to be about 3 centimeters. So the way we represent this vector, okay, I'll call it V for now. So the vector, okay, would be, well, we said 3 centimeters, 20 newtons, so 60 newtons. Okay, and now how do we describe the direction? Well, this is where we can use east, north, south, west in order to describe the direction. So this is not going along exactly one of the cardinal points, okay? But what we can do is say, well, if we start at the east direction, we can then use an angle to represent how far from the east it is. So say this angle here is 30 degrees, we would say east 30 degrees north. So this first cardinal point represents where we start, okay? And the second cardinal point represents where we're going to. So east 30 degrees north. Of course, you could also represent this as north 60 degrees east. Okay? We tend to try to use the smaller angle if possible, but what we never do is we never use an angle greater than 90 degrees. Okay, so we would never say west 150 degrees, east. And even at that, you see the problem. Does it mean in this direction or in that direction? So always keep our angles in between 0 and 90 degrees. Okay, so this is a nice way of describing it because we can imagine north, south, east, west in our heads very nicely, and it explicitly gives us the magnitude. I don't have to go actually measure it with a ruler every single time. All right. So let's move on to this next question. Okay, now again, you might stop the video for a second and ask yourself what this might mean. So if you want to do that, you can do that now. Okay, so now we're going to try to talk about the idea of the angle between two vectors. What might that mean? This is where we also want to go to this idea of what the definition of a vector is exactly. So definition of a vector says a quantity can be described with a numerical value and a direction. So if I take this vector here, okay, and I want to determine an angle to that vector there, well, it's not too clear how I'm going to compare these two vectors. But I want you to think about what actually a vector represents. It represents a numerical value, which would be the length, and a direction in this direction. Okay. Well, the great thing about defining vectors this way is it means the position of the vector is of no importance. So I can take this vector and I can move it. So one, I think, obvious option would be to move it there. Okay. Does this vector have the same magnitude? Yes, because they're the same length. Is it pointing in the same direction? Yes, it is. So these two vectors, and of course this is going to help you in number 4, it would seem as though these two vectors are one and the same. Okay, and this is one of the most important qualities to get about vectors, is their position on the plane is of no importance. The only thing that's important is the length, the magnitude, and where they're pointing. Okay, the other option to describe the angle between vectors, well, would be to place it here. And this is actually how we choose to represent the angle between two vectors, is we place them what we call tail to tail. So this starting point is called the tail of the vector, and this ending point is called the tip of the vector. Okay, so what we do is we place them tail to tail and we find the angle between them. Now notice that this could also be considered the angle between them. So we have to choose one of the two. Not surprisingly, we choose the smaller one. Okay, so the angle is the angle between two vectors. Okay, is the angle. Okay, and specifically between 0 and 180 degrees, okay, when they are placed tail to tail. Okay, before we end off part 1, I just want to make a couple of points here. So first of all, we are seeing that we're now talking about angle in terms of degrees. So now we got to do a little turnaround because we just spent a whole course and a half talking about angles in radians. Well, here we're going to go back to talk about degrees. Okay, we'll have a chat about that later on. Okay, so second of all is this idea of referencing a vector represented by an angle as tail to tip, okay, and being able to place the vector wherever I want. So as long as I keep the same magnitude and the same direction, I can move a vector anywhere on the plane. Okay, so we'll stop here and part 2 will be coming up shortly.